computer. MLBBQ is starting. Go.
So thank you for meeting with me today. I'm going to talk about tips and tricks for machine learning. I tried to gear this talk towards stuff that's useful for fMRI and DWI processing, but a lot of it is also just generally, hopefully useful. And there are some Python examples if you guys ever want to go back and look at it. The topics we'll talk about are data and pre-processing, normalization techniques, training strategies, evaluation, and CV, as well as garbage in and garbage out and ownership. And then there's some supplementary information at the end if you guys want to look at it on your own after the references.
So you are using your laptop, but we are looking at this.
Oh, yes, this is true.
What's the plan?
There we go. Oh, thank you. Thank you.
Yeah, if you can
So
click
these are-
OK, it will disappear from our field of view.
Oh, thank you.
Perfect.
All right. So there's data pre-processing normalization that needs to happen per subject. And after you train test split, you always want to fit the normalization on the training fold only to prevent data leakage. And so depending on the data that you're working with, for instance, raw T1 intensities vary across sites and they vary across each recording. And so you want to normalize them. Whereas other measurements are from 0 to 1, and so you don't need to. But for raw T1, you definitely do. And so to prevent data leakage, you want to continuously ask yourself, could any of this information in the test set accidentally influence the training data? And if so, make sure that doesn't happen. You want to avoid data leakage at all costs. You always want to perform quality control. It's really important to log everything that you do. Reviewers might ask later, which subjects did you exclude, for instance, because of motion or scanner artifacts, and you want to keep a record of all those IDs so that if you ever publish, you have them. Log everything because you might, in order for things to be reproducible, you want to log everything.
Can I maybe interject something? So for
Absolutely.
the neuromark data sets in particular, Zenning is often the one who does the exclusion criteria and stuff like that, does a lot of normalization and stuff as well. So oftentimes the normalization and stuff that he does is per subject, so it doesn't, like he's not doing like group normalization.
Yeah.
But definitely in the exclusion, if you do need that stuff, ask Zenning where it is and he can provide it to you. It's often enumerated in the folders, like how he did it, what he did. He has scripts, but sometimes it's not like clear where to find them. But for neuromark stuff, that's often already done for you. So just to be aware.
Nice, thank you. Yeah, so frame displacement is fMRI specific. It's a measure of how much a subject moved between each time point, and it's computed from the 6 motion parameters. Generally, if the subject's moving too much, that's no good, so you don't want a great frame displacement. Ghosting happens in DWI, and it's basically a visual artifact. And so we have an example of what that could look like with MRI, coronal projection of the eyeball movements. You can see there's like some artifacts. So you want to, look through your data, make sure that's not there. But I guess sometimes that's already done for us, which is awesome. There's another type of normalization you want. You can do per subject, but then you can also do a normalization that takes the so for instance, so the min-max normalization we talked about before is a pre-processing step, and it operates on, for instance, voxel intensities. But then group norm is another normalization that's inside the neural network that's applied to the feature maps. So that's different. And so you can also do group norm. We just learned in our personal project recently that it was super useful and it worked really well. Use group norm if you can, as opposed to batch norm. It's always a good idea, and it's stable for small batch sizes. That's another reason why it's really great. Please, yeah.
Can you explain how group norm differs from the batch norm?
Yeah, so batch norm is over a batch of subjects, so that's like a bunch of scans all together. whereas group norm is over the channels. It's common in fMRI data to split into 64 or 32 channels just because that's how many bits. As far as I understand, that's why those, but really you could choose whatever number of channels. And then each channel is like a part of the data. It's like split up into these sections. And so if you were to normalize over a single channel, then you can lose inter-subject variability. And so that's why they do like two channels. So you normalize over two channels at a time. But that's because the different channels are of such different scales that still is able to um, preserve the information and normalize to that
I
scale.
don't know where that's coming from. Every time we used it, we normalized them by channel, and it works great.
Single channels.
And
Oh, okay.
yeah. But also, I don't think it's the best norm conclusively. I haven't seen a proof.
Oh, okay.
Like I don't
No.
trust your results yet.
Oh, okay.
I mean, seriously, it's like we need actual. Yeah. So, but yeah.
Yeah.
Armina has an evidence that it works for
Yeah.
segmentation problems and things like that. So, but the thing is, batch norm is in a sense unrestricted. Like it's unbounded.
Mhm.
It can grow like the mean that it's computing, the running mean and average. It's unbounded, and it can shift anywhere you want per layer per batch, not per layer per batch, but per layer per training. But group norm is practically z-scoring for those of you who have ever done anything with data. Yeah, and the scoring keeps all the values constrained and only the relative changes matter. And when we're trying to extract information, relative changes is what we care about. We don't care about higher or lower. It's like derivative, right? The higher or lower has no meaning. Why would we store it? When we store higher values and let them affect the data, then we can quickly run out of the FP32, forget it, even if you like FP16. So your range, new model becomes numerically unstable, basically. Like you require more range than you actually need with batch norm. That's easy to get into that situation. So if you don't know anything about numerical stability, but you're a hippie modern boy who knows about how that can happen, I know it can happen. People know about quantization, but know nothing about numerical stability. But then let's like think about quantization. It's not going to work because you need to quantize such a range that just doesn't fit. You either don't recognize the small values because you choose quantization into 4 bins, or you cannot capture the large values because the difference is big. Yeah. So basically, my comment is group norm that worked for us by one channel z-scoring independently. It's also called instance norm if you do it only one channel. It's totally fine. So this do it by twos, I don't know where it's coming from. We don't see that in practice.
Oh, interesting.
And
Okay.
another thing is, do you even need to do group norm? That's questionable. It worked again for us in segmentation models, but every time when somebody tells you use this in machine learning or any empirical field, don't trust it. There's never a right answer. You're not getting a silver bullet. You will have to suffer through your problem and decide what is good for it. It's like the rules of thumbs, it's a lie. It's just like they don't work.
Yeah.
Like one thing about machine learning is like if one could just press a button and solution would be obtained for you, it wouldn't be an experimental science. It would have been a solved problem packaged and sold in Walmart on a frozen package aisle. But unfortunately, we're not, or luckily, we're not in that business.
I have another. Oh, so go ahead.
Well, I have another question about group norm. I wonder how it works mechanically. So
This core each. So if you have
what are the channels?
It's
Is it
a
like
kernel.
channels in CNN outputs or something like that? Would be, what's the
It's
channel?
a kernel, right?
channel for CNN.
Yeah, so like you one channels and you normalize each channel independent from the others.
You score each channel independently, yes.
Yes. Okay.
So ignore its geometrical structure. Assume it's just a time series or whatever. It's a set of data points, one-dimensional. Compute the mean, subtract the mean, compute the variance, subtract the variance, divide by the variance. There is another trick that I don't know, I haven't done thorough experiments on that, but it either way works, I guess. You multiply each channel by a constant by a learnable constant. So even though you normalize the variance away by z-scoring, if the model really needs it, it can get it back by this multiplication factor, but like overall. And you add a learnable constant. So if it really needs to shift it, it kind of defies the purpose of the quantization and numerical stability. That, like in a sense, like if it shifts two channels too far apart, but it can solve your subject non-detectability problem.
Oh.
But then I'm very skeptical about detectability based on magnitudes. Magnitude is not a signal in what we're doing. It's like if they only different in magnitudes, it's just too easy of a problem. It's not like it's not a pattern.
For bold, you mean for bold?
For anything.
Yeah.
Yeah, for anything, not just for fMRI or
Yeah.
brain imaging. If it's just magnitude, it's just a baseline. No, you didn't normalize your data. You chose the wrong baseline. A pattern is more about information. It's from information theory. The magnitude shift. It's that integral constant. It could be anything. It doesn't matter.
Yeah.
Okay.
And you use both sides of the distribution, right? So it's not just the magnitude. It's the whole distribution. So you're not square rooting it, right? So it's
when you normalize both sides, yeah. But you're not working with the data anymore. This is internal models representation.
yeah.
Yeah.
Okay.
Well, but in a sense, if you're using ReLU, then you are automatically destroying the negative part. If your nonlinearity is ReLU, and you're doing this and then passing it through ReLU, which we do, then you are getting rid of the negative part.
I see. Okay. Thank you. That was.
Yes. And yeah, it works. That's all I can say.
Got it. I'll trust you.
Oh yeah.
Yeah, I guess maybe it doesn't always work. In our case, it helped for 100 subjects, but it still hasn't run for the whole data set, so to be decided, hopefully. Fingers crossed.
I don't know why you say that. I'm sorry. I've looked at the
I'm always pessimistic. Right?
Joan's results don't support your words even for 100 subjects, right? Joan had the same result with batch normal.
Yeah, similar.
Yeah, like very similar numbers.
With the standard
Well, but if
deviation.
my parameters are different, then it's like all of mine were the same parameters except for just the norm. So everything else was held constant.
The results are the same like with batch norm.
No, not in the PowerPoint. It was better.
Well, okay.
Well, we can talk about it later.
That's
Yeah, we can talk about
a
that.
separate.
Yeah.
That's a separate work.
But I'm hoping it's useful. I think.
I'm hoping too. You have a slide on. Don't trust yourself, right?
Right. That's true.
Mostly, who lies to you is you. So the first person to be skeptical about it is yourself.
That's always true.
You're the only other person. First is yourself.
Yeah, so there's different strategies for learning rates. So you can warm up your learning rate with one cycle LR is one type of curve that you can use, or you can use like a cosine decay. And so the idea is that you increase the learning rate linearly for the first certain number of epochs, and then you let it drop. And there's it's basically prevents, as far as I understand, like if loss is exploding, learning rate is too high, and basically doing this curve thing prevents unstable gradient steps, and it prevents loss explosion. So this kind of like keeps it bound somehow. I don't know if Sergey has more advice on this, but these learning rate strategies that we use.
No, otherwise I have stories. So it's just
Yeah. Okay. And
Yeah, I think one big thing I see a lot with learning rates is people don't often understand, and you mention it in having the batch size effectively halves the LR, but there are a lot of other ways you can also scale your learning rate inadvertently. Often when you combine optimization functions, for example, do like various forms of regularization, you are implicitly changing your learning rate. People don't think about it.
okay,
batch size,
nice.
as you said. Did you mention that the batch
Yeah,
size?
it's one thing there, but there are a lot of things that can do it other than just batch size. Like I see it a lot with multi-objective optimization, things like that.
Oh, but the effect is the same, by the way. What happens in batch size is every sample in the batch has its own gradient in that multidimensional space. So, and they slightly point to a different direction. When you have multiple objectives, each of them has its own, like it's not a single direction. In any angle, any cosine distance shortens your step in a sense. Like it moves you away from the direction. So the more vectors you're averaging, the shorter your effective learning rate becomes. So you need to compensate for that.
Yeah, I think writing out the learning rule that you're using can really help clarify like where you're effectively updating.
Nobody does that.
Otherwise, I'm like, what am I doing?
Yeah, you because you're a philosopher.
I guess.
If you're a behaviorist, at least try 500 things and choose the best one.
Another important topic is handling class imbalance, and there's different ways to deal with it. You guys have probably heard of stratified k-fold, but one that's maybe to me is lesser well known was this pause weight. So basically, you just divide the number of your groups by each other, and that's your weight. And then, so for instance, if you're classifying like males versus females, and you have less males in the data sample by 1.63 more females, then for each male classification, it will carry a 1.63 times larger penalty. And so that sort of helps with the class imbalance. And, it's important to report AUC and not accuracy.
Can I also interject something about the k-fold?
Please.
So this is a very good point for class imbalance, but it also applies to continuous variables, right, and distribution imbalance. So I see it a lot with brain age prediction, right, where you have you might inadvertently have a very old, set of batches, or your training sample might inadvertently be very old if you don't split in a way that stratifies by distribution as well. So like the sklearn stratified k-fold, you need to quantize your labels first in order to get a decent stratification, because it doesn't handle continuous labels. But it's also something to be wary of with regression problems, not just classification.
There is a deeper discussion here, but I forgot the exact references. But back in 2018, I looked at this problem with neural networks versus like regular small sample size, and the literature that I saw there with examples, literature again, just the papers that people are trying, that you don't need to do anything for neural network in this case, because the neural network, the softmax and everything needs to learn the imbalance. It will, like, if your data set is large enough but it's imbalanced, it will know, it will just calibrate the confidence levels on the less frequent class and things like that. So I don't know if it still holds or people discovered that was just the wrong intuition at the time, but
I think the issue is more in like things like cross-validation and train test scenarios, right? So if you stratify your data in a way that doesn't, like if you have a training subset that has a very different distribution than your test and your validation data sets, you're going to get like wildly like weird reporting. Like you might have a validation data set that is way more imbalanced than your training data set. You want the relative balance to be the same, I think, is the issue that I've seen more than I have seen also the imbalance thing with neural networks, but as long as that balance is consistent between your training, validation, and test sets, then I think that's the thing to more be aware of.
So this talk in general is conflating two things. One thing is how to be honest, and another thing is how to train a model.
Yeah.
And so what Brad is talking about is how to be honest,
Yeah.
and that's statistics. How do we actually evaluate the model?
Yeah.
And most of machine learning is about mistakes and evaluation.
A lot of it.
And then the other things like learning rate and things like that, learning rate scaling is about how to train a model, but that's those are unrelated issue. And so
Yeah.
for training a model, class imbalance doesn't matter. Or like if you have
that's
enough,
involved.
if you have enough data, just go with your data, whatever your data tells you. But when you test the model, make sure that what Brad said, that you're not helping the model by giving it an easier test than you will actually see in the wild, like those people in Zero Teeth and lost $500 million, right?
Yes,
Whatever you
yes.
can talk
Yeah, there's, yeah. All right, so evaluation metrics and reproducibility, very important. Always try to, when you can, use bootstrap a confidence interval. So that's important. So you're not reporting just a single AUC. You can create a confidence interval instead. You can compute the sensitivity and specificity, and AUC alone is basically not enough. So you basically always want a confidence interval if you can. Also set seeds at something standardized, so you have reproducibility. Reproducibility is really important. If you can't reproduce after your reviewers ask you to, then that's no good. So again, log everything. We said this before, but again, that's really important. You can save your model best paths, and you can save your test IDs, and remember to save your subjects that, which IDs you used and which
Save your
ones you didn't
seeds.
use.
Nobody saves the seeds.
Huge issue.
No.
I have like
I don't save the seeds.
I reject so many papers based on not doing spacing stuff. Yeah, it's really important. I don't know if you're going to mention it later, but about the seed thing as well. Are you going to talk about like random model initialization and lottery ticket hypothesis stuff? Or?
No, you should mention
Okay,
that. Yes, that's important.
So, I am always pushing for not only. I think fixing a seed is the minimum. You definitely should do that. I reject papers on not doing that, not reporting that. The next step above that that I think people should be doing is multiple initialization, so multiple seeds for initializing. Thing. Also, multiple seeds for validation if you want to do for multiple cross-validation seeds. And the reason you want to do it for the model initialization in particular is this lottery ticket hypothesis paper, right? That you can just randomly end up with a much easier model to optimize, just based on your loss landscape and all this other stuff. You can, with the right initialization, you can train a lot more efficiently. And so you might not be honestly reporting how someone in the wild with a totally different initialization might be able to train.
This I disagree with.
You disagree?
I disagree. Yes. So from the following sense, what are they selling? If the paper is talking about, hey, we got a model that is easy to train, that's one thing. If the people are saying, with this model we can achieve this result, then what you're saying I disagree with, because that's a separate research.
I disagree. I disagree with your disagreement because it depends how they're reporting. If they do all the baselines themselves and do everything consistently within their own framework, then I agree with you that one seed is sufficient, right, to show performance.
It's like they found a way to get this model to perform, and maybe other people will not be able to find that way, but that's another problem. Like this model work quality if you initialize it like that.
Sure, I think that it's more honest to, especially if you're showing improvements over baselines that you didn't implement. If you're taking a baseline from another paper, it's due diligence to do multiple initialization, show the general case, right? And if you do show the best case with a particular optimization, then you need to be very transparent about that. And I think doing multiple initializations is good. If your performance drops below your baselines, then you can maybe make an argument for how particular initializations are needed for this kind of model, but it ends up being a weaker paper than I think. It depends on the context, right?
Yeah.
But I think it's something that I don't see done enough that people like. I'm seeing it more at NeurIPS, but I always
But the problem with it is when they run it on a single data split.
Yeah.
and report just the best data split.
Yeah.
Then yes, that's
Yeah.
clear. But initialization is a different beast. So
It is.
if with the same initialization strategy or seed, but on different data split, on different data distributions, you can demonstrate that it works, that it not hallucinated, inflated just one single number because of a lucky split. Then I think you're fine. It's just like, okay, well, this is the initialization that worked. The magic seed 42 is the only thing that we could get to work, but it works in any distribution of
Yeah.
data. I'm fine with it.
Yeah, we can maybe argue back and forth. I disagree. I think I already gave my case, but I think especially if you're showing performance improvements, like, and especially where it's marginal, like you're only like 1 to 2% above a baseline, like I think you really need to do your repeated initializations as well to show that it's not a fluke of initialization. And if it is, you need to be honest about that, right?
Well, maybe the initialization is part of your method.
Well, yeah, and that's fine.
It's-
But you need to be transparent about that, and I think people are just not transparent.
Well, by the way, initialization not mentioned at all here. Besides in
Very
this argument,
yeah.
it can kill or make your training go well.
Yeah.
It doesn't matter on the architect. It's not your architecture. It's not anything. But this is for training. This is not for evaluation. If you initialize incorrectly, your skip connections, all of them may be clogged, and you're back in 1986 trying to train your network with backpropagation with vanishing gradients.
Yeah.
The same model can be perfectly trained if the parameters are initialized correctly, and it could be fastly trained, you could waste a lot of computational power and nothing will work. Initialization is not random. But yeah, the better quote would be random initialization is not random. Like you have to very carefully think about what you're doing. And it's kind of logical, but there is a lot of theoretical research as well on how to correctly initialize the models, in which bounds the weights should be, and things like that. And for numerical stability, there is a thing, I don't know if it's mentioned, called weight decay, is when you're training with this annealing, when your learning rate is low and low and low, you also need to push the norm of your weight down as well. This is
It's just L2 regularization.
It's opposite to initialization. It's like you have to treat your weights carefully in the beginning and at the end of the training. They're different, but both of them are very important of how good will be a model. And I don't know. It's not that it's not being talked about. It is being talked about.
It is, yeah, quite extensive.
People reading a lot of papers and things like that.
I think for these big LLMs too, it's a thing they think a lot about because they want to get the best initialization possible before they invest a ton of money into the training, right?
Yeah, and it's not random. It's like by looking at the architecture, you can see, oh, okay, if I do it this way, then skip connections are just not working. Their biases are, or only skip connections are working and nothing else is working. And yeah, so a lot of thought should go into that, or at least some. And then trial and error, 500 different things. As long as they're different. If you're trying 500 times the same thing and it doesn't work, blame yourself.
I actually have the same problem. In like 80% of my experiments with different seeds, it works very well, the FPSA project. But in like 20% of the time that I use different seeds, it's real fragile and complicated.
Well, maybe we're not initializing correct.
Did you just both pick a 80-20 because of the
No.
No. Okay, sorry. You actually, okay, sorry.
No, like 90%, 80%, something like that. And it's weird.
It is weird.
Yeah.
It
Something
really
about-
affects the performance of.
Yeah. So that's interesting. We need to look into it. Maybe it's initialized incorrectly. I don't know, Xavier, Gaussian, and how the biases are set. How you set the biases initially also matters a lot. Do you set them negative or to 0? And lots of consideration. Depends on architecture and things like that. And we're working with something not very well understood, right? So we need to think about how initialization should be done there. Sorry.
No, yeah, this is great. It's like a ML podcast. It's good. So with small cohorts, you always need cross-validation. A single train test split with 50 subjects gives you a result that's most entirely noise. With 100 subjects, if you do a five-fold cross-validation split, that gives you 5 independent generalization estimates, and then you can report a mean plus or minus a standard deviation. The critical thing is to do it at the subject level, not the scan level.
There is a big issue with all of that too. When you're reporting mean plus and minus standard deviation, you're making an assumption that your distribution is symmetric, particularly Gaussian if you're doing two tests after that. And mostly if you're pushing the boundary to the top AUC or whatever metric, it is not symmetric. It has a fat tail. Most of them are good, but so this logic doesn't
Huh.
quite
So what do you
apply.
do?
The field does.
No. People are talking about it. Recent paper by from Thomas Yale group. Basically, if you are using like even when you're doing cross validation, that's a slightly different topic than this. But when you're doing cross validation, usually we run tests like with Pavel. We love doing that a lot. Figures are full of statistical tests on box plots, and we're using non-parametric testing because distributions are not symmetric. So the parametric testing doesn't apply, or it's not that good. Parametric Gaussian-based testing doesn't apply. But when you test two distributions, one against another, and you in cross-validation, the folds are dependent. Like each fold, they're not independent samples. They're dependent because you split the same data, and if a fold is in testing, then it surely is not in training. And if it was in testing here, then it surely will be in the training in the other run. So those runs and cross validations are now dependent. So your samples, your one result, one AUC value is a sample. So your samples are now interdependent, and that will not inflate the mean value, but that it will inflate the variance. And by inflating the variance, it will inflate potentially false positives. But of false positives of this method is different from that method, even though they are not different. And when, as Brad said, you have only 1% improvement, you're like, my method is statistically significantly better. Oh, but did you do this correction? In this case, it matters. It's like they're as good in terms of the mean performance. But when you're starting to claim I'm better when you're very close, then you need to. Statistics is big lies in statistics, but it's so like statistics is very difficult. People.
How lactocritic is it? Like I'm trying to visualize the distribution. How so it is a factel, right? So is it
It's more closely like it's trying to climb up, and so if you quartiles box plot, the median is above.
Okay, got it.
So it's most often. It depends. Sometimes it's so bad that the median is below,
Gotcha. Okay.
and it's trying, but it's not like the median is not in the middle.
Yeah, got it. It's not symmetric. Yeah.
It's not symmetric. Just be careful. Cross validation is a heuristic. It is not a God-given truth. Like it's a heuristic. It's like there is no proof that it works like all the time or things like that. It's just a way for us to not be wrong. So don't say it's like, oh, it's on a pedestal and I'm doing cross validation, that's why I'm good. No, just got it. It's a specific heuristic that you're using to try to be honest to yourself.
So like in a proper ML, we should show what kind of distribution it's coming from, ideally. Maybe.
Ideally, we should be transparent about everything.
Yeah.
But
Very important slide. Garbage in, garbage out. Always look at your data. It's a really old computer science principle that's very relevant to neuroimaging. Your pipeline can produce volumes that are technically valid tensors, but scientifically meaningless. A failed registration, a normalization that's divided by 0, or a subject that's scanned with different parameters will throw everything off. The model will train on all of this and give you a number. And the quality control snippet here takes about 30 seconds to run and catches the most common issues before you waste hours of GPU time.
Don't even run anything. Look at your data. It's a brain, after all. Why would you run something blindly and trust that it gives you a number? It will lie to you. Oh, because I mean, a beta particle hit the CPU, and I don't know, Soranga was messing with it. Well, whatever. Like, look at your data. Maybe you're running on chipmunk data because Armina misplaced it by mistake. How do you know? Look at it first.
It's a lever.
We don't look at the data enough.
Yeah, that's the coolest
and
part of
it's
the
just-
stuff that we're doing. Is looking at the brains. I think you gotta
Yeah.
do that.
And when you look at the brains, like your grandparents may think you're doing actual work.
It's true. I've been in coffee shops. People are like, what are you
Yeah. I'm just like I'm just procrastinating, and then, oh, this is your work.
To drink caffeine because I showed a canister brain. He was like, "That's what happens if I drink caffeine." I'm like, yeah.
Oh, that's cruel.
6 months later, he was like, "I don't have caffeine." I was like, "No way, really?" Whoops, I got you're fine. You can drink caffeine.
Yeah, that's cruel.
Yeah, so yeah, always visualize your data and some of the things that can go wrong with the MRI scans, like they could be a chipmunk and then they could be, like motion is common, but then there's also stuff that's less obvious, like heartbeat. There's like dental, like metal in your teeth will affect the way that the brain.
Magnetic susceptibility or whatever it's called, and then it's just like a flash flare on your brain instead of.
Yeah. Like there's a lot of things that could go wrong, so you got to look at all of it. Another way to visualize stuff is look at, look at your classes, not just for class imbalance, but to see what's going on. Like, are there any obvious outliers? Like, always continuously look at your data as you're processing.
Yeah, always good to do some scatter plots and stuff on your labels. And like, I miss that. We don't do a lot of I used to do a lot of R-based data exploration before. You can do a lot of it in Python now.
The classical anecdote is they took two groups of statistics or some kind of data science students and gave them a data set like a CSV with two columns, and because it was at the end of the course, and so they asked those groups to apply what they learned from this course, means and variance, whatever, to look at this data and analyze this data. And I forgot what they told one group and versus another, but one group just went ahead and started applying all of the fancy tests and statistical metrics and things like that. And another group plotted those data as X and Y coordinates, and it was a teddy bear. And when they had to answer what was remarkable, the most remarkable thing about this data set, that statistically inclined group was like, oh, it's like no linear correlations and blah blah blah, and they're like, look, it's a teddy bear. And so if you don't look at your data, you will never find out it's a teddy bear. You will just see the mean and variance, and maybe AUC that is not so good, but good enough, maybe. And
Yeah. Always own your results. Ownership means being able to explain every single section in your results section. And this is really important. And in the current era of auto ML and large AI models, it's very easy to run a pipeline and get some clean looking results without actually understanding what's going on. Ownership means you can defend what you're looking at, and defend your results. So you know why your AUC is 0.72, not just that it is 0.72. You've looked at the distribution of your predictions, you know which subjects the model has struggled with, and you have a hypothesis about why. The pipeline did not produce your result, you did. Take responsibility for understanding it, and don't let the fact that a tool, whether it's a pipeline or an AI assistant, generated the output be the reason to stop thinking critically about what it means.
Yeah. So please never tell me, oh, this is what Claude told me to do. That's like it's just a cop out. It's like, I don't care about who told you to do that or who you hired to do it. You are the responsible party. I don't want to hear about LLMs or anything. It's like, it gives me zero information. Claude told me to do, it just tells me, okay, well, go back and do it yourself then, or until you're confident in the results, I don't want to look at it. But until it's you confident, why would I check Claude? I can ask Claude, myself, or like, people reading your paper as well. Oh, Claude told you to do this in your paper. Well, then that's not interesting. We cannot ask Claude ourselves. Why do we need you to write this paper? Yeah. It's like, it doesn't mean don't use Claude or any other LLM. It's fine. It's a tool, but you are the responsible party. It's the ownership part. Why did you use it? Why did you trust it? It's the same thing as with me when I say grad student did this work, but I'm responsible. Like, why did you trust this grad student if you knew that things could go wrong? Sorry.
So we got horror stories from Zillow. Zillow, the house sales thing, you guys know Zillow, yeah. They built an automated system to buy houses directly from homeowners, make improvements, and resell them for profit. And at some point, the algorithm predicted the algorithm predicts what the house is worth, right? And then it automatically buys it, improves it, and does this. And they were doing that with real money on real homes, based on those predictions, buying thousands of homes. And the failure was that nobody was critically examining what it was actually doing in the real world. And the predictions looked reasonable on a dashboard, but they were wrong. They were systematically overvaluing homes and markets that were starting to cool down. And by the time they noticed, they gained 500 million in losses, which resulted in them firing 25% of the company, which is like, it's a lot of people. It's a really, really big oops, $500 million oops. And that was for overestimation.
So it learned the inflation. Is that what it was?
Yeah, like
Sounds like there was systematic bias that they just didn't discover, right?
yeah, they were overvaluing some region that was actually like the price of the market there was starting to go down, but it was systematically overvaluing it, so they threw all this money into something that wasn't worth anything.
When did this happen?
I think early, like
2017-ish.
yeah, around 2020 somewhere, yeah.
It's hard.
Not very
You
long
hear
ago.
so many stories about the sources of bias, and it's, I think, impossible as a human to be aware of every possible source of bias, and it's possible even with very thorough data exploration to be aware of all sources of bias. Certainly,
Well, you need to be aware that you're not aware.
yes, I think that's the biggest thing.
There's something there. Like, don't trust any numbers. Like, I mean, if 500 million depends on, and it's you. The only way is to put your money on it. Yeah, to make you responsible.
And that's just 500 houses now in Atlanta.
They're all in Atlanta. It's all of Atlanta. Yeah, so that's it. Our key takeaways. Maybe group norm is not always better than batch norm, so let's cross off that first one.
Well,
No.
before we go key
Yeah.
takeaways, online people and people in the room, do you have your own horror stories when you had to like retract the paper or had to recompute everything the day before submission because you understood that you like always return true as correct, or like you did like
I definitely.
do you have your
I
own
can-
stories when you like discovered at the last moment, or maybe when it was too late and you didn't tell anyone?
I think one of the first times I switched over to working on depression data, I was inheriting a data set from Solomon, who was a PhD student who used to work here, and I wasn't very familiar with the data, and it was very, very highly imbalanced, and so it turned out that it was not a problem, but very early on, I realized that you could just get almost comparable performance to what he had reported in one of his papers on with a random model because the data set was so imbalanced, or not random model, but a single label.
Yeah, single
model.
label.
Right.
You just predict the majority class.
Yeah, exactly.
And that's it.
Yeah. So that was something that it was a near miss because I thought that he hadn't tested for that and done stuff, but I ended up talking to him about it. He was aware of that and was able to show me that he had divided the data set up enough that it was balanced. But it's just that was a very near miss. That was not my paper. But I was like Shaman, you might need to return your paper. He took it very much in stride. He
Yeah.
was very anxious about these things.
There were other stories. Zillow is a weird story, but they're more down to earth. I don't know if you did a deep research on that, but I've read something on the Dropbox blog about them almost releasing a model and then figuring out that it like it it's not telling them what they think it's telling them, and it's, yeah, but it's very common.
These are some links to some of them. There were like this pneumonia asthma prediction pitfalls. There was like an oncology LLM that was suggesting.
Yeah, you have this Dropbox story there, yes.
Yes, yeah. So you guys can go look at these if you went after.
I know. I read on Dropbox blog. I read a very insightful blog post on Half Transform, is how they initially were detecting the documents, and it's really well written. It's very simple. I worked with Half Transform in 2001 or something, but then I kind of didn't think anything much about it. But they are useful. But simple tricks. Besides the failures.
Yeah.
Sorry.
Half transform is to detect straight lines in an image by looking at the dual of the image where each line is a dot, and so if there are multiple, each dot is a line, each line is a dot in that dual representation. So if many dots, which are lines, intersect at a single dot, which is a line, then there is a line. It's a beautiful mathematical trick, or signal processing trick. HOUGH, half transform. Read about it. Yeah. Another beautiful thing for historical fact. It's completely unrelated, but I learned about it today from a book. I was listening to a book. Is that the steam engine governor in every talk and every conversation on modernity, what is credited with invention of the rotational centrifugal governor, and how the modernity started from it as the industrial revolution. And nobody credits the actual inventor, the Huygens, who's from like 100 years before that, invented actual thing, and what just borrowed it. I mean,
Really?
The invention was there. Huygens is not credited.
Oh.
Huygens is a visionary that nobody credits enough. I think he was the first one about the wave. Like he studied waves, light waves, and other waves, and things like that. It's just like,
Right.
anyways, let's move on. It's just a.
I want to maybe say we are kind of out of time almost, but these examples from medical imaging, I think, are the best ones to kind of help contextualize our research as well. It's very, we didn't talk too much about, you talked about some pitfalls, but what these pitfalls can mean in terms of actual harm to people is, I think, important to remember. Not only, is systematic bias bad in terms of you're not getting a paper published and, doing that kind of thing, but systematic bias is bad in terms of, actually hurting people. You can cause a lot of harm, especially with the large generative models. I think there's been a lot of evidence showing that, there's a lot of risks to these things.
I heard a horror story today when you have a CT machine in the hospital and you just need to do a low power CT, but instead you turn it onto the cancer treatment mode for the patient who just came for a routine exam, and they're coming out with hair falling down.
No.
It's just like it
Oh,
happened.
wow.
Yeah.
That's bad.
This is for you building your models. Do not allow other options like besides the one that, just do not.
Well, I think being transparent about the risks is the most important thing. One cannot control for all possible risk, but being aware of possible risk and communicating those, I think, are the most helpful.
And also a helpful advice in your own life as well. You are lying to yourself. I am lying to myself. We all are lying to ourselves.
All I know is that I don't know anything.
Yeah. It's like when you're just, I mean, anything. Yeah.
Not me, I'm
Yeah. It's just be aware. We're such a good self-deception machines.
That's true.
Like, well, about not just about you, about it. About it. Okay, well, thank you. I don't know what was that about. Why did you decide to give this talk?
Comments in the chat.
Oh, do we
Oh.
have comments? I thought
There's
those
like
were...
TJ's here.
TJ, you
Hi,
should
TJ.
just talk.
I didn't want to interrupt you guys. You guys are having a nice conversation. No, but yeah, I review a lot of machine learning stuff at Georgia Tech too, and it's just one thing that I've always seen and is always controversial is how you choose K and K means, and however you use K means in whatever method. There's just always so much noise, and it is so divisive. Big thing is always test a small ball around whatever K you have just to show if the results are super different or not. But yeah, I always push that for supplemental sections and papers I review. Um, yeah, and then pre-processing is always a big issue. I've seen more often than not other students run like 100 subjects on their self developed pipeline, and they just don't look good at all, and it's because they missed a step in pre-processing. So always good to have a second pair of eyes before running long runs with pre-processing.
We didn't really talk about hyperparameter optimization, but that's
Oh, true.
definitely a big point.
Op
Because when you do your
Optuna.
hyperparameter, yeah, when you do your hyperparameter optimization, exactly what TJ said. If you're still getting improvement, don't stop. Like continue your search. You got to show the peak right of your optimization.
Well, there are many of those. Aptuna is one of them. Yeah.
But I think with capable cross validation, that's not as important. Like this, I don't often treat that as a hyperparameter. If that's what you were referring to, TJ. I think you could just pick a K, and it makes sense for your data.
Yes, but he was talking about K-means,
K means,
right?
yeah, so hyperparameter optimization.
But for K-means, it's again, you cannot treat this. Machine learning is a weird, well, it's like statistics. There's a lot of theory actually, but theory is dead without practice. So you cannot be doing one or another. You have to like for K-means, keep increasing K, and your feet will always be increasing. That's talking about you always will get better until your K equals the number of samples, and then you're saturated. You're doing the best. So there are many situations like that there. So you have to be aware of what are you actually optimizing when you're increasing K. What does the likelihood function mean? And like yeah.
I've read, is this true or not? I want you guys to confirm something about choosing K around the sample that is the minority class in the balance of labels. They choose,
Cross-validation again?
yeah, with the K. Like, how do you choose K?
For cross validation.
Yeah.
Heuristically, because you're accept that you are doing.
Yeah.
So choose it heuristically and say it like I chose it because of this.
Yeah.
But then as TJ was saying, but then when I switched to a lower value and higher value, I couldn't reproduce my work, and so probably I should go back to the drawing board.
Yeah.
The result is still stable, so it's not sensitive to K. Okay, well, but then now we're talking.
Mm-hmm. That makes sense.
Something like that.
I have a clarifying question for TJ. Are some of these papers that you don't like, are some of these clarifying papers that you don't like using like elbow criteria, or is that an acceptable heuristic?
So in most conferences that I've seen, people using things like caps or using things like elbow method for K, it is never an elbow. And if you go do a lot of the noisy data, we never see an elbow. So a lot of times they'll do a percentage of change, threshold change. So it's even another order of statistical inference that you're trying to make off the data. And so it's just picking apart noise that you think is okay. And then once you choose your K, you have so much post hoc analysis that really stems on that singular choice in your pipeline. And so it's just very hard.
Okay, nice discussion, and thank you everyone who participated. If we don't have any questions from online, thank you, Lisa, for presenting, and I will see you next time.
Thank you guys. Thanks everyone for your participation.